Hello and welcome. In this video, I'd like to go through a derivation of the Gompertz equation for modeling avascular and vascular tumors. This is actually more of a review of a paper because this paper does a very beautiful job of deriving this model, and credit goes to Marcus Beinhammer for this paper. So first of all, let's start off with, and I encourage you to read this paper as well. But I'd like to just get into the derivation of this model because it's cool and it's interesting. And at the end of the day, the model looks like this. This model highlights the growth of a tumor, and this is the change in volume of that tumor per unit change in time. And this model looks awfully messy in that there appears a natural logarithm, which is a ratio of the volume, natural log of the ratio of the volume to this constant k. And there's another volume over here, so it's very curious where this model came about. But if we start at the beginning, and we first of all make some assumptions. So this model assumes a spherical tumor. Okay, so we can't get away from the fact that this is a spherical tumor. So if we think about, well, that's not what we want. If we think about this as a spherical tumor, we'll try that one more time. We'll think about this as a spherical tumor, and that means that, maybe not perfectly spherical looking, but close enough. Okay, so we have a spherical tumor, and therefore we have some properties of the spherical tumor. For example, we know that its volume is 4/3 pi r cubed, and it also has a surface area. Right, so surface area is the amount of matter or material that would be required to wrap up the insides of that sphere. So the area equals 4 pi r squared. Okay, so these are two formulas involving a sphere. All right, so we start there, and what we want to know is what is the change in volume per unit time. So the volume, we're not restricting ourselves to any specific measurement of volume, just some sort of cubic units, and time, we're not limiting ourselves to a particular unit of time, we're just saying it's some unit of time. Now we're also going to make some other assumptions. We're going to assume, and this is an important one, that the growth of the tumor is limited by nutrients and or oxygen which enter through the surface. So that means that this formula is going to be some function of area. That is, right, because you have all these nutrients that are going to penetrate this surface, and that's what's going to cause them to grow. They're all going to break through this surface, and the more surface area you have, the more area you have exposed to which the nutrients and oxygen can make their way in. But the problem with this model right here, that we assume that the rate of change, the rate at which the size of the tumor changes per unit time is a function of area, is going to be a little bit problematic because our dependent variable is v and not a. So the argument that Mr. Beinhammer makes in this paper is that v and a are related in the sense that if you take v to the 2/3, this symbol here means is proportional to, and is proportional to just means that it's a scalar multiple of. And let's see how that would work. So if we look at or investigate what v to the 2/3 is, there's v right there. The volume is equal to 4/3 pi r cubed, so that's raised to the 2/3 power. Now when we raise something to a power, if it's a product of numbers, each of those individual numbers gets raised to the same power. So 4/3 raised to the 2/3, and pi raised to the 2/3, and r cubed raised to the 2/3. First of all, this 4/3 pi, that's going to become some mixture of these values here. It looks like it's been kind of reduced and reorganized, but we can rest assured assume that that component is 4/3 pi raised to the 2/3. And then there's another pi there, so let's not worry too much about that. But if you raise r cubed to the 2/3, we multiply powers, so 3 times 2/3 is 2, so you get r squared. Now, we said that v to the 2/3 is proportional to area. Well, area is 4 pi r squared, and we see in here that we have a pi r squared here, right here, and we have a pi r squared over here. So we can see that this quantity and this quantity are just off by a factor. This has a factor of 4, this has a factor of that messy thing there. Okay, so a well-known tumor model based upon this, now that we know that your change in your volume is going to be proportional to your area, well, let's just write this as dV dt, right? So there's dV dt is proportional to area, right? Because v to the 2/3 is going to be area, and the change in volume is going to be proportional to that. Now, one little interesting or curious thing that we can do here is notice here in the second step, there's division by v of t and then multiplication by v of t. Now, that might seem redundant and unnecessary because those two do indeed cancel out, since they are the same quantity, and we're assuming that the volume is not 0, therefore we can divide by the volume. And so it reduces to this model here, a times v to the 2/3. Now, if you look at the function a times v to the 2/3, if you were to plot look at different values of v, and then you looked at the curve av to the 2/3, it would look something like this. And so that's going to produce unlimited, albeit slower, but unlimited growth. And so this is called the Mendelssohn Model, and that assumes or describes unlimited growth of that tumor. That's not necessarily what we want, because a tumor in the early stage, at least, so we're focusing here on the early stage, I'll highlight that in green again to state that this is an assumption, has a sigmoid growth curve. Now, a sigmoid growth curve is just a fancy name for an S-shaped logistic curve. So this is what we call a sigmoid or logistic curve. Okay, meaning that we cannot follow this model further, but we've got to make a modification. Now, if you look at this ratio here, now v to the 2/3 is not exactly the area, it's simply some scalar multiple of the area. But if you notice what this here is, this ratio, this is a ratio of, roughly speaking, area to volume. So this quantity here is known as the AV ratio. Now, yes, again, they do cancel out, and this does simplify just to this, but we're going to do something really cool here. We are going to say, in order to do this, we can't assume unlimited growth, because that will just assume that the tumor blows up without bound. Actually, the solution of what we're really plotting here is dV dt on the vertical axis. So this is just how the rate of change changes. But if we actually plotted this, v versus t, for that model, it would be some sort of exponential growth. Now, if we approximate this AV ratio, and what we mean by that is if we can come up with some sort of approximation for what happens to this ratio, then our approximation will likely have some error in it. And as long as we err on the side of this quantity being less than it actually is supposed to be, then these two quantities don't directly cancel out, and this rate of change will start to become smaller and smaller. How is that the case? Well, first of all, area to volume. If you look at the area to volume, if we were just to divide the area by the volume as such, then you would find that we have 4 pi r squared over 4/3 pi r cubed. And so we do some cancellation here, and that r squared cancels out. That becomes r to the first, and the a to v ratio becomes simply 1 over 1/3 r. Now, as r approaches infinity, as r gets larger and larger, as the radius of this tumor gets larger and larger, then AV approaches 0. So your area is going to grow much more rapidly than your your volume is going to grow much more rapidly than your area. And as a result, that ratio is going to approach 0. So if we approximate this and it's slightly smaller than what it's supposed to be, then this will approach 0. And what happens when something approaches 0 in your rate of change model? Well, if this factor approaches 0, even though this is going to be a constant A, and this is just the volume of that tumor, this ideally will become close enough to 0 where it will essentially give us a 0 rate of change. And what that will do is that eventually, once that volume gets kind of large, that the rate at which the volume is going to increase is going to get smaller and smaller. Okay, so enough of some of that setup there. So what we're going to do is we're now going to focus on the A to V ratio. So focus on A-V ratio. And we're going to approximate it. Now, one interesting series approximation, so series is just a way to say, how do you approximate a number or a quantity? So, for instance, if you had some number raised to a negative power, then you could approximate it as a series expansion. So, for example, if I wanted to do something like 2 to the negative third, or better yet, if I wanted to do 2 to the negative third, one way to approximate that would be to say, okay, well, this is going to be a sum of infinitely many terms, but when we approximate something, we usually skip a few terms, right? So let's just say we just look at the first term. Well, the first term in that sequence is going to be negative k, so negative 3 times ln of x, in this case x is 2, all of that raised to the n power, so n in this case, this is just the first term, so n to the 0 over 0 factorial, and that comes out to approximately 1, right? Because anything raised to the 0 power that's not 0 is going to be 1, and 0 factorial is 1, so this comes out to 1. Now 2 to the negative third, if you take 2 to the negative third, you get 0.125, which is clearly wrong. And that's the reason for that is because this is an approximation. Now, if we do the n equals 0 and n equals 1 and add those together, so now I do negative 3 natural log of x, which is still 2, but now this gets raised to the first power divided by 1 factorial. Now if you add those two terms together, negative 3 ln 2 comes out to negative 2.07, negative 2.079. And you can see that the difference between those is still erroneous because we said this is exactly 0.125, but the series just says you have to keep adding terms onto it if you want to get more accurate. So now if we did plus negative ln 2 squared over 2 factorial, that's going to come out to, let's see, squared divided by 2 comes out to 2.16. Okay, and if you continue adding these terms in there, then you are most certainly going to get closer and closer to that approximation. So you can see that if we add these three numbers together, we still don't quite get 0.125, but we're getting closer. And more terms, there'll be positives and negatives in this. This will eventually, if you continued adding, and you continued adding here, you would get exactly 0.125. Now this series comes from a Maclaurin series. So a Maclaurin series is usually a well-known series from Calculus 2 that some people encounter. And they just show that this comes from a Maclaurin series where one of the cool things with these series is that we rewrite x to the negative k as e to the negative k ln x. So basically you're exploiting this quantity and making it what you want. Anyway, you can walk through this derivation and see that this series does in fact work, and that's what he's proving here, that it does in fact converge. So what that means is now our model, our dV/dt, when we're just focusing on the a times v to the negative k. Now you might say, where did v to the negative k come from? Well, back up here, when you look at this model, v to the 2/3 over v to the first is going to be v to the negative 1/3. So you have a times v to the negative 1/3 times v, and you can see that these still multiply. If you add their exponents, it's still going to give you v to the 2/3. So what we're trying to do is we're trying to estimate that v to the negative 1/3. Okay, so if you have v to the negative k instead of x to the negative k, that just means you're going to replace x with v, and that's exactly the same formula. Now, with this exact term, all the way with the infinite terms in it, it just reduces down to this formula right here because it's exact. It's the Mendelssohn model. But if we don't use all of the terms in the series, but instead, let's just truncate the series expansion and approximate v to the negative k by keeping only the term of degree less than or equal to 1. Okay, so what that means is that degree less than or equal to 1 will have negative k ln of v over 0 factorial to the first power, to the 0 power, plus negative k ln of v over 1 factorial to the first power. And so this to the 0th power, that should not be in the denominator as well. That should just be in the numerator like so. And so that won't make much of a difference in this case. But this will give us 1 plus negative k ln of v. And so if you have a times that, right, a times v to the negative k, which is equal to this, and you distribute the a in there, you'll have negative ak, and a times 1 will just give you plus a. All right, now we're going to make some substitutions in here. We know that k is in fact 1/3, but we're not going to actually put in the 1/3 right now because we're going to substitute the symbols. We're going to define a times k to be equal to b. So all that does is just makes the equation simpler because these are just some constants. So that right there, I'm going to call b. 1 over k, we're going to call c, and capital K, we're going to call e to the power of c. K will always be designated as the carrying capacity below. Therefore, equation 5 becomes, well, how did we get from here to here? Let's think about that a little bit. It's a little bit easier to see how we get from 6 to 5 than from trying to go from 5 to 6. So let's just try to see how 6 ends up starting off as 5. So we said b is equal to, so we're going to go start at 6, equation 6, which is negative b ln of v over k. And so now we can make some substitutions. Again, all we're trying to show is that 5 and 6 are the same equation. So b is equal to ak, therefore I can replace b with ak, natural log of v over k. Now, one of the properties of natural logarithms is that if you have the log of a ratio, it's the difference of the logs. So ln v minus ln k. And now k, capital K, is defined to be e to the c. Okay, so negative ak, natural log of v minus natural log of e to the c. And natural log of e is 1, so this gives us negative ak, natural log of v minus c. And then c is equal to 1 over k. So this is equal to negative ak, natural log of v minus 1 over k. And we know that 1 over k is defined, 1 over k is defined to be c. So distributing this out gives us negative ak, natural log of v, and then distributing ak to negative 1 over ak, the k's will cancel out and we'll just get plus a. So this is exactly what equation 5 is. And you can backtrack. You can also follow, since these are all equal, you can follow from 5 up to 6. Start with 5 and get to 6. But it's a little bit harder because some of the substitutions are not super intuitive. So there is the Gompertz differential equation. One thing to note here is that if k is some constant, then an important idea is that the natural log of 1 is equal to 0. Well, how does that help us here? Well, if v, as v, let's say v starts off as 1 and k is 3. Well, the natural log of 1 over 3 is going to give you a non-zero number, right? But now what's going to happen? Well, now if the tumor has grown a little bit, if we assume that the tumor is growing, then now let's say it grows to a volume of 2. Well, that's still not equal to 0, but notice that the ratio is getting closer to 1. So as the volume gets closer to the denominator here, then this is going to be approximately 0. And if that ratio becomes 1 and this becomes 0, then your tumor stops growing. And that's what's going to give us this effect of the tumor kind of doing something like that over time. So the fascinating part about this is that for I equals 0, we get, or for I equals 1 rather, if we only use the first, so by the way, where this all comes from here is we just estimated a times v to the negative k, and a times v to the negative k was the result of this ratio here. So we still have a times v in this model. And so that's where that v came from. It's the fact that we still had one. This is our approximation for that a to v ratio. And of course this goes to infinitely many terms, but if you only go to I equals 1, this is an error. This has error in it. It only estimates the AV ratio. And since it underestimates the AV ratio, or rather, since it estimates the ratio, there's going to be some error in it, and so you get the limiting model, you get the limited Gompertz growth law, and for I equals infinity, well, for I equals infinity, then you get exactly the AV ratio, and the V's cancel out, and you get unlimited growth. So based on how many terms you have in this series expansion, we only went with 1 to get the well-known Gompertz differential equation, but had we had infinitely many of these terms, we continued to expand this sum out and go just beyond the first degree, we would actually end up with the Mendelssohn model, which is a times v to the 2/3. It's a very beautiful, beautiful derivation, beautiful process, making some assumptions and using some really cool mathematical properties and features. There's also another way to do this, and you can also approximate the AV ratio by using binomial theorem and using that kind of series approximation. I'm not going to get into that here, but if you're interested, you can continue reading on in the paper and just see that you get a slightly different looking model out of it that essentially does the same thing.